Question number 1. Calcium carbonate decomposes when heated as shown. The enthalpy change of reaction for the thermal decomposition cannot be measured directly. That means you can't do this experiment in real life while measuring the temperature change, where you have to use Q equals to MC delta T. Instead, a procedure involving 2 experiments is used. In each experiment, the enthalpy change of a different reaction is determined. So the first one is we will be using calcium carbonate with HCl to form calcium chloride. This is another reaction. Okay, so we can see calcium carbonate reacts with 2 HCl to give your calcium chloride and H2O and CO2 like this. This is called delta H number 1. Okay, now in the lab, right, you can just take a particular mass of calcium carbonate, you pour it into the acid, and then you can measure the temperature, okay, before adding, after adding. So this one is doable in real life. And let's look at experiment number 2. Experiment number 2 is similar. You take calcium oxide, you react with HCl, so this part, plus 2 HCl to give calcium chloride and H2O. And this is called delta H number 2. So let's look at the procedure. Experiment 1, we weigh a 0.05 sample of powdered calcium carbonate, transfer 50 centimeter cube of an excess HCl. So I want to take note that this is an excess HCl into a small glass beaker. Start the timer and measure the temperature of the HCl in the beaker every 30 seconds for 2.5 minutes. So when you measure something every 30 seconds or every 1 minute or every 2 minutes, we call this a continuous assessment or continuous measurement. All right, continuous measurement is because you continuously want to find the number or the data out. Okay, so you have to have certain interval. So the interval inside here will be 30 seconds. So the step 3, right, is to measure the HCl alone for 2.5 minutes and see how is the temperature of HCl alone first. Okay, after 3 minutes, we add the sample of the calcium carbonate into the HCl, continue measuring the temperature of the reaction every 30 seconds for a further 5 more minutes. All right, so that will be step 4. And if you look at experiment 2 is to repeat experiment 1, but we use calcium oxide instead of calcium carbonate. So part A suggests why the enthalpy change of reaction for the thermal decomposition of calcium carbonate cannot be measured directly. Okay, the answer is because you cannot measure temperature change while you are applying heat, because when you are conducting the thermal decomposition, so this is your fire here, this is your calcium carbonate. Okay, so you will liberate CO2 gas, and then perhaps you want to go and capture it. Normally in practical paper, you want to capture it in the lime water over here. So how are you going to measure the temperature? Because when you are providing heat to decompose, the thermometer reading of course will increase. Okay, so that's the reason why you cannot measure the enthalpy change of the thermal decomposition. In fact, any thermal decomposition, the enthalpy change cannot be measured is because you are already providing heat. Okay, so that will be the correct answer. If you want to see what I've written back then, I said because there is no solution or water involved in the thermal decomposition. My argument was because of when we want to calculate heat, right? Q equals to mc delta T, where m is the mass of the solution. So I was looking at the setup of the thermal decomposition, right? There is no solution in it. All right, so that was my initial answer now, but obviously I was wrong. Okay, I think marking scheme answer has a higher weightage to this. Part B1, calculate the mass in gram of calcium carbonate to be weighed using 2 decimal place weighing balance in step 1. Since you wanted 0.05 mole, you multiply with the molar mass of calcium carbonate. The mass should be 5.04. 2 decimal place, your answer must land in 2 decimal place. Okay, next. So outline how a student should weigh by difference. Weigh by difference means before and after, using a weighing boat in order to determine the exact mass of calcium carbonate added to HCl in the beaker. Draw a result table with appropriate headings ready for the student to complete. So let's just look at the table first. table, I wrote mass of weighing boat plus calcium carbonate, mass of weighing boat plus residue. I want to change the word residue. Okay. I would say mass of weighing boat after pouring or after transferring out. Okay. I'm a little bit like skeptical now with the word residue. Reason is because residue can be the final product form from the reaction. So if you just want to look at before pouring and after pouring, there is still some more calcium carbonate left. It is still calcium carbonate, but it is remaining. All right. So to not confuse other people, rather examiner on what is residue, because residue can be something else than calcium carbonate. In this case, maybe they can start thinking that your residue is a calcium oxide. Yeah, so I think it is best to go something like mass of weighing both after transferring or after pouring, all right, and then mass of calcium carbonate used. Now, if we do look at the marking scheme, the table, mass of both before transfer, calcium carbonate, mass of weighing both after addition or after transferring or after pouring. Okay, now you look at the heading. They said residue of calcium carbonate. They never write residue alone because residue alone is questionable. It could be the calcium oxide product that was formed, all right, because not clear ma. So if you want to use residue, I suggest you use residue of calcium carbonate. That means it's still the reactant one. Okay, so that's why you see me trying to change my result headings. And then lastly, mass of calcium carbonate added. And then if you look at the instructions, draw a result table, that one fulfill, outline how a student should. All right, now outline. So I said weigh 5.01 of calcium carbonate in empty weighing boat, transfer the calcium carbonate into a small beaker, weigh the weighing boat and residue of calcium carbonate. Okay, like this. But don't trust whatever I write. Let's look what marking scheme says. Number one, weighing both plus calcium carbonate is weigh. Okay. Then after that, number two, weighing both is weigh after calcium carbonate is added to HCl. I think basically, right, they just want you to write the order. Can you see the order of weighing? All right. This is title headings with units. The first mark is the order. So I don't think my answer, now when I really look at my answer, right? Okay, I don't think I will get fully. Okay. Maybe I won't get fully. It's because I realized that you won't be weighing 5.01 instead. You will actually weigh the mass of a weighing boat plus calcium carbonate first. There's a order in line, and then you can use the word and then weigh the mass of a weighing boat after transferring. Okay, so one mark is to look at the order in the sentences, and the second mark is the heading. Okay, so we go on to very detail. Okay, hope you are clear on that. Part C, identify which piece of apparatus should be used to measure the volume of HCl. HCl was assessed, and if I remember clearly, the HCl over here was in 2 decimal place. Now, the only apparatus that we are used to that can weigh up to 2 dp in terms of volume is your burette. Okay, so what happened here is excess, normally we will use measuring cylinder, okay, because it is in excess. All right, but marking scheme says burette, all right, is the answer, as we need 2 decimal place to get the exact mass of this calculation. So let's look over here. Burette and burette measure to nearest 0.05. There is an N because they say identify and give. There are 2 things. So identifying is 1 mark. Burette is because burette can read up to 2 dp, because then only you can get full 1 mark. Okay, now I would like to explain like why burette is needed over here. I know that if you've done a lot past year, usually for excess solution, right, we can use measuring cylinder. Even in paper 3 also, we will use measuring cylinder for any volume that it is in excess. But why this particular paper needed a 2 decimal place, which is a Buret final answer, it is because when you do the calculation, Q equals to MC delta T, where M is the volume of the H cell in this case, then the number here would be as accurate as 2 decimal place. Even if the volume is accessed, the accuracy of that volume is also very high to 2 dp. You can have still a 50 centimeter cube using a measuring cylinder that is accessed, but the accuracy is low. So therefore, because of the 2 dp, we need to use Buret. So in my analysis, right, decimal place precede, okay, decimal place will precede or has higher importance, all right, the access or not access condition. This is after doing a couple of few paper 5. We will allocate the type of apparatus mainly following the decimal place as the priority first in line. Okay, so because all the while we go by, okay, access is our priority. We made our decision based on access or not access. But now I think we gotta make our decision based on the decimal place first. Then only access, not access is a letter issue. Okay, yeah. So I hope this part is clear enough for you. Let's look at part donkey. Without making any changes to the apparatus, suggest an instruction to be added to step 3 and step 4 to make the experiment more accurate. So can we look at step 3 and step 4 first? Start the timer and measure the temperature of HCl. Okay. After 3 minutes, add the sample of calcium carbonate and continue measuring the temperature. How can you make it more accurate? One thing is missing, stirring. Okay, stir the solution to make it more accurate. There's only one answer out. All right, if you look here, stir the mixture or stir the solution. Because normally we will use the thermometer to stir, if you can recall from your practical paper. Okay, because otherwise if you don't stir, right, then the reaction occur very slowly. Remember, when the reaction is slow, remember this, heat loss to surrounding will be very high. Therefore, the number you calculate out will be very different compared to the theoretical amount. Yeah. So in other words, to increase accuracy, you want to increase the rate, because increasing rate will have lesser heat loss to surrounding. That is a legit answer. All right. So based on one question, we can figure another thing here. All right. So in other people, right, they ask, how can we increase the accuracy? So many answers gives you like basically suggestion of how can you increase the rate, be it you increase the concentration, all right, or be it you use a lesser volume of solution. So perhaps these people will ask, not sure. We shall continue and see. Now part E. A student carried out experiment 1 and obtained the result given in table 1.1. Okay. Now the time that you add the calcium carbonate, you cannot take any reading because you're too busy adding it. All right, you don't have enough hands. All right. Decimal place for temperature reading is always 1 dp. Okay. Now plot the graph on the grid in figure 1.1 to show the relationship between temperature and time and use a cross. Remember, cross, please don't plot too big now. Plot teeny, weeny small. Okay, don't your diameter of the cross, please don't use as big as this diameter, the smallest one. I try to go smaller than the smallest box diameter. Okay, now the points and line of best fit for the data before 3 have been drawn for you. So normally, I think this is also another question here in maybe other paper. What is the purpose of measuring the temperature for the first 2.5 minutes? Okay, for me, it is to actually check whether the lab environment, okay, which is the environment, is stable in temperature or not. We hope to see constant reading like this, all right? Because it means that for 2.5 minutes, the lab environment has a constant temperature of, 19 degrees Celsius in this case. Therefore, if the temperature reading starts to fluctuate, it is entirely due to the reaction's contribution. That means not environment contribution. It's solely the experiment contributing to it, because otherwise it's not accurate. Okay. Now, if you get your 2.5 minutes data, we're talking about general discussion here. If let's say your 2.5 minutes, the temperature reading is up, down, down, up, up. Now, in this case, we can see that the lab environment, the temperature is not constant. Perhaps you want to get away from the fan or from the aircon, that causes the thermometer reading to fluctuate. All right. Because if you continue to run this experiment, when your first 2.5 minutes has fluctuation in data, it means that after that, when the temperature changes, right, part of the temperature reading is also contributed by your lab. And the problem now is you don't know your lab contributed how much of the temperature for that particular reading. All right. So to get rid of this, normally we require you all to do a 2.5 minutes of so-called checkpoint, whether your lab is stable or constant in terms of the temperature. And then draw a line of best fit for the data after 3 minutes that will enable you to determine the theoretical temperature. Theoretical, this part. Theoretical. That means you need to extrapolate back. Extrapolate. Theoretical means you do it on paper to backtrack. Okay. Now, versus experimental. Experimental is the highest. If we look at the table here, right, this is the experimental highest temperature. All right, the highest temperature. And this is any one of here is the experimental lowest temperature. So you can just take highest minus lowest. That will be your delta T. You can do that. All right. But that will be not so accurate lah. Okay, that is not accurate is because when you plot a graph, right, you can backtrack and account for heat loss to surrounding. I hope by now you know the difference between enthalpy change setup. There are two types of setup. One is continuous, where you take the reading every 30 seconds and you plot a curve or a line. The second one is no-need graph. Just sit down, take initial, pour the calcium carbonate, and take the final temperature, which is the maximum one. That is your experimental highest temperature. It's an easy way to do because you don't need to monitor. You just need to sit down there and check the highest thermometer reading. You record it already. But that experiment, right, could not account for heat loss that was lost to the surrounding. But if you do a graph like this, you can. So if this is the case, I want to show you what it means. This is my highest temperature, which is 36, as you can see. Okay, so if you were to just take experimental number, this would be your delta T. This line will be your delta T. But if you plot a best fit line, we call this a cooling curve. Cooling curve. So cooling curve, yes, it's a straight line. I know we use the term curve, but it's a straight line. Okay, because the temperature tried to equilibrate back to your room temperature, which is 19. Again, it makes sense that they try to equilibrate back to the original temperature. So that's why it's called cooling curve. So when you draw an extrapolation, and at minute 3, you need a straight line here. So this is the extrapolation dot, okay, from the vertical line at minute 3, and then you backtrack because this diagonal line here is to follow the trend and to backtrack for us at minute 3 what would have been the highest temperature, because at minute 3 you won't get any thermometer reading. First and foremost, your hand is busy adding things in. Second, there is not enough time for the calcium carbonate to react to give you the highest temperature because it needs time. Okay, so this is to backtrack. So therefore, the difference over here, okay, if you do theoretical, this is your temperature change, which is delta T. So the difference between doing a graph and not doing a graph is this particular section here in green. Okay, this partner. So it's this line to this line here. So this particular bubble, which is the temperature, this is accounting for heat loss to surrounding. Because as you can see, if red color, you only can capture this much of temperature rise. But if you backtrack using a graph, you can capture more temperature change. All right. And the difference between the two is actually the heat that was lost to the surrounding. So that is a more accurate way of analyzing the experiment, actually, to plot a graph. But that is if you do a continuous setup where you continuously measure every 30 seconds or every 1 minute. Okay? So this is how my curve look like. Now next, use your graph to determine the theoretical temperature increase at minute 3. So we want to look at the extrapolation. So mine over here, if you look on the left, is 38.25. Now, one more thing, when you read, right, okay, you will realize that my intersection point is in between the grid. The most we can do is to read in between the grid, okay? So this is reading from graph. The most you can do is to read in between the grid, which is half. Now, some of you will start asking, but if my intersection, if let's say is the first 25%, but it's not on the grid, or the bottom 25%, okay, not the half of it, this is half, right in the middle, okay, the green one. So if let's say your intersection is the top 25 or the bottom 25, right, you have to make a decision whether you want to read it as the middle or you want to read it as the bottom grid line or the above grid line, because you cannot be reading a 25% of the smallest box. Reason is because, first, for you to even read in between, you are making an error here already. All right. And if you want to read half of this box even smaller, okay, I'm trying to zoom in a bit more for you to see. I think that's the maximum I can do. Okay, nice. So if let's say you want to read here, which is half, okay, of the red and the black line, right? If you want to do half, right, that means first you got to read a red color line, which is make one error. Then you got to read in between to create another error. So you make 2 times error when you want to read the 25% top version or the 25% down version. All right. But that is the correct way to do it. If you want to read 25% on top or 25 below, first halve it, and in that half, you halve it one more time. Okay. So when you do the percentage error calculation, you got to take the reading 2 times. The error need to multiply by 2 times. Now, but this is the correct way to do, but normally we don't do that. Okay, it's because you're making the error twice. So when you make the error twice, right, it means that the reliability or the accuracy of the number read is actually quite low. For us to even beat half of the grid like me is already having one error made already one. What more if you want to make an error on an error? So you're going to make 2 times error. But if you really have to make it, which will never occur in Cambridge chemistry paper. If you really have to make it, I'm talking about outside of Cambridge chemistry paper, then you please declare clearly that you made error twice. Therefore, when you calculate the percentage error, you have to multiply your error by 2 times. Are we clear? All right. But coming back to chemistry syllabus, right? Normally we don't read half and the half of our original half. We don't do that. Okay, so for me, I read it as half, which is 38.25 minus my initial temperature called 19. Therefore, my temperature change is 19.25. Okay, next. Suggest why the temperature measured at 3.5 is lower than the temperature measured at 4. So at minute 3, you put the solid in, which is the calcium carbonate. There's no reading here. Then at 3.5, the temperature increased because it's exothermic. Then after that, the temperature continued to increase at minute 4. Then after that, it start to show a decrease. So the question now is why 3.5 has a lower temperature than 4? It's because the reaction is not completed yet, right? It is still in the ongoing process of reacting. So they give them some time to fully react. Okay, so I showed because not all the calcium carbonate has reacted or the reaction has not completed yet. It hasn't unleashed its maximum capacity yet in its time. Okay, now G. A student carried out an experiment 2 and determined the temperature increase of 62 and the heat release by the reaction Q is given by the formula. Thank you so much for giving us the formula. Where M is the mass of HCl, remember M is only the mass of solution. I don't want to see the mass of any solid in any history. Okay. Assuming that 1 centimeter cube has a mass of 1 gram and that the specific heat capacity is 4.18, calculate Q. So Q equals to M, which is 50 centimeter cube of HCl, 4.18, and 62. All right, therefore you get the heat in joules. Therefore, you go and divide by 0.05 moles of the calcium oxide. All right, and then you can calculate what is the enthalpy change. Since the thermometer reading increase, it means it's exothermic. Therefore, I will put a negative here. I'll put a negative here. So far, okay, Okay, next. Use the energy cycle below and answer to G and the information given for the thermal decomposition. Now, enthalpy change for experiment 1 is minus 84. Okay. Oh, so nice. They give it to us, minus 84. And if you are unable to calculate a final answer in G, which is experiment 2, you may assume the value of 179. Okay, but because I managed to calculate the number here, which is minus 259, therefore I put the number here minus 259 over here and here. So direct equals to indirect equaling to Hess law. Okay, so you should be able to get an answer of positive 175.16. Okay, now I want to address things like, Miss, if I wasn't sure about my answer on top here, can I still use the answer here? The answer is no, because you check the statement again. If you were unable, for the fact that you already answered up here, be it the right or wrong answer. So let's say the answer is wrong, then you just lose mark here lah. But when you go to part H, you must carry your answer forward. Must. Okay. And you cannot use the 179 just because you are lacking in confidence. If you really have to do and take the 179, I suggest you leave this empty and get the maximum loss in terms of marks. Then only you have a right to use 179. But I'm pretty sure you all are not in this situation. So I suggest you just take whatever you calculate and carry forward. All right, they will give you error carry forward marks. So please take your number and don't be scary cat and take the 179 given by examiner, because they already say if you're unable and this is not the correct answer already. Okay, now part I. Identify the main weakness of the experimental procedure and suggest one improvement to overcome the weakness. And the main weakness is not the type of thermometer used, because some of you will say that let's use a thermometer that can read up to more decimal place. All right. But they don't want the kind of answer. All right. Is there any other suggestion that we can give? All right. Number one, when it comes to enthalpy change of reaction, right, normally heat loss to surrounding is the biggest weakness. Okay. And then if this is an enthalpy of combustion, usually it's like, because the combustion was not completed. That is if it's a combustion experiment, but this is not combustion, This is a desolvation. Okay, a desolvation of a solid into an acid, right? So you cannot use that here. So the only way out is heat loss to surrounding. So how can we improve, all right, or minimize the heat loss to surrounding? Number one, use a polystyrene cup because you use beaker. Okay, you should have detected it at the first place really. Okay, second thing, you use the lid over here. Okay, let's see the marking scheme. Is there any other alternative to this? Only these two. Okay, only these two. Wait, I repeat again. One improvement to overcome this weakness. Okay, I'm just curious, right? Can we suggest things like things that increases the rate? For example, since HCl is already excess, can we use more mass of calcium carbonate or calcium oxide? So for example, I want to use 0.06, okay, of the calcium carbonate, or instead of 0.05. I want to use a higher mole, all right, so that when you have more, it increases the rate. So when the rate increases, okay, heat loss to surrounding will be decreasing. All right. Or maybe the other thing is another suggestion that I can think of, even though it's not in the marking scheme, are things like can we increase the concentration of the HCl? Okay. I don't know what's the concentration they use. We can check back up there. But for whatever they give us, we want to increase the concentration, but we still maintain 50 centimeter cube, but a higher concentration. Because a higher concentration, the rate will be faster. Therefore, heat loss to surrounding is lower. All right. But it's just an idea suddenly I have in my mind, right? If I will accept this kind of answers, because they never said suggest an improvement in terms of they never limit us. They never limit us whether improvement must be apparatus based or must be a procedure based, because it's an open question. So long as it is an improvement, that means we can write lah. So I'm just thinking whether can my answer be accepted without checking too much. Actually, my answer is still correct, but it's okay. Just let's see what happened during that particular year. Okay. Many candidates gain full credit for the idea of heat loss being the main weakness and introducing insulation, either using a lead or using a styrofoam cup. Some candidates opted to improve insulation by sealing with a bung. This was not acceptable as one of the product is gas. Okay. Now, they never mentioned about the increasing rate to type of improvement, right? I think they will be accepted, all right? But why is the main answer things like polystyrene cup or use a lid? I believe that is the main answer is because it was very obvious that you're using a glass beaker already. So maybe they just want the obvious answer to be the answer. But it doesn't mean that using a higher mass of solid or using a higher concentration of acid cannot be accepted. All right. Yeah. And I guess that because majority student can answer that, right? That's why they never want to address the minority, lah. So I'm not so sure how many of us will actually write that, which is to increase the rate. But just in case, if you want to write that, I think that is acceptable. All right, let's move to the next question. This question is about an experiment to investigate the effect of temperature on the equilibrium of K1. So Fe3 plus and thiocyanate. This is called thiocyanate, SEM. Okay. Now the data collected is to determine the value of the enthalpy change of the reaction, but we want to see the effect of temperature lah. Okay. Now to set up the equilibrium, iron 3 is mixed with potassium thiocyanate, and iron thiocyanate have red color. Just so you know, I know it's not in Cambridge chemistry syllabus. The specific test for Fe3 is thiocyanate. It will give you a red color. Specifically, is the blood type of red. All right. I know it's not in your syllabus, but I'm just telling you. All right. Since you're looking at this information. Now, a colorimeter is to measure the absorbance of the reaction mixture. So colorimeter starts from the word color and meter. They are used to measure how intense the red color is formed. It can be any color you want. You just need to press the colorimeter to detect what color you want. So in this case, we will set the meter to detect red color. Okay. Now, a calibration graph can then be used to determine the concentration of the iron thiocyanate in the reaction mixture. Now, solution A, B, C, D, we have thiocyanate and iron. Concentration is given as such. Describe how you would prepare 100 centimeter cube of solution B from solution A. Solution B, it's a lower concentration from solution A. So that's why we need to do a dilution. So when you want to use dilution, you need to take out the formula called M1V1 equals to M2V2. Include a calculation of the volume required and give the name and capacity of any apparatus that should be used. So initial concentration is 0.0092. How much of the 0.0092 in terms of volume you need to take out to form a diluted 0.002, and the total solution is 100. So therefore, I calculated the volume is 21.74 according to the calculator. All right, but in the lab, you can't measure 21.74. You either go by 70 or 75 because your apparatus cannot read 0.1, 0.2, 0.3, 0.4, 0.6, 0.7, 0.8, 0.9. So you please choose. So what I did was I went down to 0. Okay, but I think that marking scheme should be correct and I'm wrong because it is better for you to go up by 0.01 to 75 because your burette reading can read up to 2 dp, correct? If I go down according to a general mathematical rule, that means I'm making a minus 0.04 error down. Okay, but well, I was not in the best of mind to think about it back then. So it should be 21.75. I don't believe it should be 21.70 now. Okay, now you have to tell the apparatus which is capacity and the capacity. So I say use a burette to transfer 21.75. Okay, 21.75. I explained why 75 and not 70 already, because 4 to 5 is making plus 0.01 error, is faster that way. Okay. into a 100 centimeter cube of volumetric flask. So the volumetric flask capacity must follow the volume of what you want to prepare, which is 100. Fill with distilled water. It must be distilled water until the mark. Stopper the flask invert to mix. If you look at the marking scheme, okay, it must be nearest to 0.05, which is this. 0.05 means 2 decimal place, in other words. Again, use the burette, transfer to volumetric flask, and top up, all right, with distilled water until the mark. Like I mentioned before, shake invert well. Sometimes they give, sometimes they don't give. All right. I suggest you give, because you really don't know whether that particular people, right, they choose to give or not. So I think it's best that you provide them in this case. Okay. Now next. This was just after that my discussion, but I think I answered already lah. Okay, 21.75 lah. Now next. Now, how do we look at the line, okay, drawn? Okay, now, before starting the experiment, solutions B and D are used to produce a calibration graph. B and D. Calibration graph means it's like a standard for us to refer. It's just like a BMI, all right? BMI 20 to 24 is called normal. 25 is slightly, slightly obese, or I don't know what's the word you call, or BMI 19 is called slightly thin or something like that. I've forgotten what the word you use, okay? It's called a standard, okay? Calibration graph is a standard graph where normal circumstances, if you have this concentration, the absorbance reading will be this much. All right. So in other words, if you want to understand in a layman term, right, it's just like if your BMI value is this number, for example, 25, 24, 24 here means normal. 23, 22, 21, all this is considered normal. 25 here, you look down here, this is called slightly heavy. Okay, so this is a calibration curve. So it all depends on you calculate your BMI, you go and check where you are, you know what your scale. If you're 23.5, you're still under the normal range. All right, so this whole thing is called normal. This one here is called slightly heavy. Then after that, the higher end is called heavy. Okay, this is called a calibration curve. Okay, we call calibration curve, all right, because I know that you all don't know what the calibration curve means. It's a standard, all right, where people used to refer. So in this case, we can see that they will know that if your absorbance reading is this much, the concentration is this much. If the absorbance reading is that much, that means the concentration is that much. So the more concentration, or the higher the concentration you have, the absorbance reading of the red color will be more intense and higher. So the darker the red color, the absorbance reading is darker or higher. Understand? If your red color is very pinkish, like pink one, which is low intensity red color, like here, 2 times 10 to the power -5, then the absorbance reading will be also low. So it's proportional one. Okay, so this is called a calibration line to explain to all of you. Now, known values of each solution are added and the absorbance for each mixture is recorded. The calibration curve is given in figure 2.1. The concentration of solution D is much greater than concentration of solution B. Hold on. Let's check. The concentration of donkey is much greater than the concentration of boy. Of course, open O2, okay, in order that solution donkey is in excess. Okay, in excess, correct, very in excess. Because if you look at the stoichiometry, right, one iron need one thiocyanate. So technically, 0.002 thiocyanate only need 0.002 of the iron, but we give them like, well, how many times more excess? I'm just curious, okay? I just calculate how much is excess here. 0.002. Whoa, they give them 250 times excess. Okay, never mind lah. They gave excess donkey, so that means now your iron is excess in this case. Suggest a reason why solution D is in excess, okay, so that the concentration is approximately constant. That was what I wrote. Okay, I say that so that when the solution concentration is so excess, any decrease in the concentration is small. Example, if your bank account got 10 million, I just took 100 from you, right? You will still view your bank account as 10 million, right? Any decrease is considered as insignificant to you. But if you earn 1,000 or your bank account got 1,000 and I took 100, whoa, there's a 10% drop already immediately. So my answer was that All right, because most of the time, right, when we want to make a solution, so-called in high concentration, in other words, excess, is because we want to make the concentration as constant as possible. All right. It's because we want to cancel off whatever factor you can bring in or effect you can bring into the reaction. Okay. And then I realized that the answer is not correct. So let me explain to you what is the correct answer first and why is it that answer. They said that so that the concentration of iron thiocyanate is known, or as all solution B, thiocyanate reacts. Okay. So I went and investigate a bit detail so that concentration of iron thiocyanate is known, or so that solution B is known. So what it means is this. According to the equation, right, currently now, your Fe3 is so excess and your thiocyanate is open 002. All right, we want to ensure our thiocyanate, so-called the limiting factor, will be all utilized. So if this is minus open 002, then the concentration of the iron thiocyanate product here will be also open 002. But we got to make sure that it is in excess. Understand? So that the limiting factor will be the controller of the concentration. Okay, so because we want to find the concentration of iron thiocyanate, all right, so we need to use whatever concentration of the thiocyanate to determine the concentration of the product, which is the iron thiocyanate. Now, for those of you who sort of agree with my initial answer, because that is for those who've done a couple of few past paper before this, all right, why is my answer not accepted? I know that you all see in other papers like, what's wrong with this answer? All right. Okay. The reason why my answer is wrong in this situation is because this kind of answer can only apply in a rate of reaction experiment. Because when you play rate of reaction experiment, right, where you have A plus B to give C, plus donkey plus E, all right, you want to find the concentration. You have the concentration of A and B here, right? And you got experiment 1, 2, 3, 4. All right. So when you want to see how B affects the rate, okay, when you want to see how B affect the rate, so for example, 0.01, 0.02, okay, so let's say it's 0.1 and 0.2. Now, you got the concentration of A, so that when the rate changes and double up by 2 times, it is due to the reactant B double up by 2 times. So the rate increases was all due to boy reactant. All right. That is provided your A is constant. So let's say your A is 0.01 and 0.01. In this case, A is the constant variable, B is the independent or manipulative variable, and the rate is the dependent or responsive variable. All right. Because if your A and B changes, for example, if your A is 0.03 and then it changed to 0.04, the concentration of A changes, the concentration of B also changed, and the rate also changed. So my question to you now is, your rate changed because of A or B? Don't know. But if you want to know your rate is changed by A or B, you got a constant one of them. When A is constant, when B changes, rate will change. So I know that the rate is entirely controlled by B. And if you want to see how A affects the rate, please ensure that your B is constant this time. Let's say 0.02 and 0.02. And whatever change, all right, whatever change in A is solely responsible in the change of the rate, because now the change in rate from 0.1 to 0.2 is entirely due to A's fault. Understand? Okay. So the reason why my answer cannot be accepted is because when you want to constant the concentration, it is because you want to see how the rate is affected by the other counterpart. So if that's the case, right, back then for me, I wanted to constant donkey here is because I wanted to see how boy affects the rate. That was my initial answer. Then I realized that, okay, I kind of understand why this answer cannot be applied here, because this whole experiment is not to investigate the rate. The whole experiment is to investigate the effect of temperature on the equilibrium constant, nothing to do with the rate. That's why my answer cannot be accepted. Are we clear? Rather, the answer should be, we want the limiting factor, all right, to control or to determine the concentration of the iron thiocyanate, because we need the concentration of iron thiocyanate to link it to the absorbance reading. Okay? I hope that's clear. All right, let's continue. Next. Part C. Yeah. The following experimental procedure is used. Half fill a large beaker with water at room temperature. Okay, I kind of draw it out here. At room temperature. Transfer 40 centimeter cube of solution B into a boiling tube. Over here, solution B. And place in the beaker of water, which is 25 centimeter cube. Transfer solution C. And place it into the same beaker. So this is solution C over here. Wait for 10 minutes. It is to ensure that solution B temperature is the same as solution C. It's the same as solution C temperature. It is to allow the two solution temperatures to equilibrate to the same temperature, which is 25. If you want 25, then you change, which they will change because they want to see the effect of temperature. Now transfer 5 centimeter cube, 5 over, you got 40, right? You transfer 5 first, all right, into solution C. Stir the mixture and record the temperature of the mixture. Okay, transfer and record. Measure the absorbance of the mixture in the test tube using colorimeter, because the minute you transfer B to C, all right, you will start to form the red color, which I think it wouldn't be too dark yet. Pink, iron thiocyanate, a bit of pink. And then the more you transfer, or when the heat is increased, I think the color will turn more red because the forward reaction occurs, right? I think it become darker red and darker red even over time. Okay. Now, change the temperature of the water and repeat step 3 to step 6, correct? So the temperature increases, the red color form will be darker, but our eye cannot judge how dark is dark, right? That's why we need to use a colorimeter to quantify for us how dark in terms of numbering. Okay, so identify the dependent variable. So the dependent variable is the absorbance. The darker the red color, the higher the absorbance. Okay, describe how you adjust the temperature of the water in a large beaker to obtain a temperature below 10. Currently now you are 25. All right, you want to make it 10. We are currently now at 25. You add the large beaker with ice cubes to lower it down to 10. Okay, that would be my utmost recommendation. I read examiner report, they say this, thermostatically controlled water bath has credit. That means not the main answer, but you're still going to get your marks as a secondary mark, is because they do go down to 10 degrees Celsius. But to be honest, if you want to hear for my opinion, right, I don't recommend you to write thermostatically controlled water bath, because machine normally is used to increase the temperature from 25 degrees Celsius one. Okay, we normally, for me, when I do my postgraduate work, I don't use a thermostatically controlled water bath to go below 25. All right, because their function, the build up of a thermostatically controlled water bath is actually not really to go down. Yeah, unless you're using a very expensive, sophisticated thermostatically controlled water bath, which I've never seen it for now. All right, but it only makes sense that if you want a machine that can go to a lower temperature, right? Then it's called freezer. But we don't do that, right? Actually, I mean, we can, but I mean, if you want to put a fridge or ice, but fridge and freezer, right? I don't think the temperature will be quite stable to per se So my utmost recommendation normally would be, if you want to lower down, just put ice cubes. If you want to increase the temperature, just tell the machine to go above 25, 26, 27, also okay. It only makes sense that we use electricity to increase the temperature. All right. For thermostatically controlled bath, we don't use electricity to decrease, even though the examiner report say it can go down to 10. All right. I think they're just giving the benefit of the doubt to the students. All right. Because it's not the students' fault to not know or to know that we don't do this in real life. Okay, so that's just my personal opinion. Maybe I'm wrong right now, because I finished my postgraduate work for, many, many years ago already. All right, so anyway, main lesson, want to go down, just go ice cube. Don't put fridge, don't put freezer. Want to go up, normally it's thermostatically controlled water bath. Another thing, controlled bath, water bath, don't just say controlled water bath. you have to say thermostatically controlled water bath. You must say that. You cannot just water bath alone. Cannot. It has to be thermostatically controlled water bath. Don't ask me why. It has to be this detailed. Okay, Now next, a student obtained the results given in table 2.2. So you can see here, when the temperature is higher, the absorbance is lower. The iron thiocyanate, we are supposed to fill in the blank, right? And we're supposed to calculate K1, right? Okay, never mind. So first, let's see what they want us to do. The value of the equilibrium constant K1 can be determined using equation 1. This is equation 1. Okay. X is the value of iron thiocyanate in mole per dm cube. Use the calibration graph to complete column 3. We need to use the calibration graph and record to 1 dp. So 0.6 and 0.42. So shall we go and look at 0.6 and 0.42? 0.6 is here. If you look down here, I got around 8 point something, or 8 point something to 9. 0.4 absorbance, it will come down here, 6 point something. All right. So I transfer the data, 8.9 and 6.2 in one decimal place. They said 1 dp. I put 8.9 and 6.2. Okay. Now then you put your x, which is the 8.9, according to the formula, 0.0010 minus the same 8.9, you square it, that is your K. I just follow the formula and I put the number in. All right. So you go according to the number that you read from your liner, okay, and record the value nearest whole number. That's why you see me in whole number here. Settle. Continuing. Another student does the same experiment for 7 different temperatures. Plot a graph and draw the line of best fit shown. Okay. Theory predicts that the relationship between the K1 and temperature is given by equation 2. Okay. So now, based on the function given in equation 2, y equals to mx plus c. This is your y-axis. This is your x-axis. So your x is actually 1 out. T lah here. This is your x-axis. This is your y. This is your plus c. All right. And therefore, the remaining here is your m, which is your gradient. Delta H is the enthalpy change of the reaction and T is the temperature in Kelvin. Explain why the graph supports the relationship between K1 and T. Why? Okay. Because a straight line is obtained that fulfills y equals to mx plus c function. Okay. They said why this graph that is having a straight line supports the relationship in equation 2. The relationship in equation 2 is y equals to mx plus c. The graph is a straight line. So why the straight line supports it is because a straight line formula is y equals to mx plus c. That's it. Okay. The graph is a straight line. Yeah. Now circle the point that you consider to be most anomalous. There were no error in measurements in the experiment. Okay. A student correctly suggests that the anomaly was caused because the absorbance was lower than expected by the line of best fit. Suggest why the absorbance was lower than expected. Okay, hold on. I'm not going to cheat. I'm going to solve it now at this particular moment when I do this recording. Okay. Let's see whether I can come up with the correct answer again. The student correctly suggests that the anomaly was caused by a lower absorbance. Okay, first and foremost, the anomaly, okay, two things, all right. It's either the anomaly supposed to be here on the best fit line, which is a lower 1 out of T, or the anomaly supposed to be up here, all right, which shows that you're supposed to have a higher log K1. Okay. Now, the question now is there's only one correct answer. You're normally supposed to be on the green color dot on the recipe line, or should it be on the red color dot? I let you think. Please pause the video to think about it. All right, and resume when you're ready. So the answer is green color because you cannot be blaming on the temperature. All right, remember temperature on the x-axis is your independent variable. All right, you already decided that you want to run it at the particular temperature, which is here. You wanted to run at this particular temperature. Just because you got anomaly, you're trying to withdraw back to say, oh, sorry, I shouldn't have run at this temperature. I should have run it at low temperature. If you can do that, right, then the rest of the data, the rest of the temperature they come out, also you might as well just go and say sorry to every reading you've taken, correct? It's more like I did run experiment at a particular temperature which I desired, all right, but I don't know how come the log K1 number appeared lower than expected. This should be the correct way. You must identify anomaly first. Then only you can explain why. If you don't know the problem, you won't be able to explain why. So normally, your anomaly is due to the responsive or the dependent variable part that was wrong. Okay, so the question now is why did you show a lower one? You're supposed to be up here, but currently now you're showing down there. Now, when I get this kind of anomaly question, I usually check back lah. Okay, I usually check back the table. So let me just go back to the table lah. What causes a lower log K1? Okay, what causes a lower log K1? So first, what I did was I go and take calculator. Okay, I backside Ichi. I take calculator. I went and log this number to come out column number 5. So when I log 107, I get 2.0, somewhere along there lah. Okay, 2.03. Now, if I log 70, I get the answer 1.84 around there. So now, based on here, the log K number, okay, the problem now, I'm trying to explain my problem. The problem now is I showed a lower log K1. Look at the table. A lower log K1 was due to a lower K1. They follow one, okay? A lower is going down, right? Lower log K was due to a lower log K, lower log K, which is column number 4. Correct? The question now is, why did your K1 appear smaller? Your K1 appeared smaller is because your iron thiocyanate also appeared smaller. Correct? From here, give here, ma. Here, give here, ma. Correct or not? So the question now is you got to explain, why did your iron thiocyanate appear smaller in terms of concentration? How come? Maybe you want to pause and think about it. Let me have a look now. Based on the above, the higher the concentration, the higher the relative absorbance, correct? Okay. Now, and then currently now, your iron thiosulfate is the red color one. Higher temperature, the absorbance, that means the concentration is lower. Okay. So they said the student correctly suggests that anomaly was caused by a lower, suggests why the absorbance was lower. It's because the concentration was lower lah. Correct? The concentration was lowered, you know, and then the absorbance was lowered, which is correct. What? That's what the student says, right? For me, I backtrack log K1 to concentration, and the concentration was obtained due to your absorbance here, isn't it? Correct? It's because you asked me to read 0.42 from the first graph, then only I got the 6.2 out, correct or not? So now the question now is why the absorbance was lower than expected. That means you shouldn't get 0.42. You perhaps should be getting around 0.52, but then now you're getting a lower absorbance than expected. That causes disaster to occur. Now, maybe, I'm not sure for now, maybe it's due to the temperature was higher than expected. Maybe. That means you wanted to do it at 55, but somehow during that experiment, the temperature was higher than expected, because what we can see here is when temperature increases, the absorbance decreases. The question now is, why did you show more lower? Is because maybe the actual temperature was higher than 55. Maybe lah. All right, maybe. So let's look at the marking schema. For me, right, I actually track back all my data. You can see I was very honest. A lower log K is due to a lower K1 and a lower iron thiocyanate concentration. This could be due to the temperature was higher than the 11 degrees Celsius of the anomaly. All right, because you got to know your anomaly is where. Your anomaly is this particular temperature here. And when I check back temperature, the temperature is um here. Okay, 284 reading. Hence, equilibrium position shift to the left-hand side. So that's why it becomes not so red. Okay, now hold on. Let me just check how did I come up with the equilibrium position shift to the left-hand side. Just give me a moment. Let me just check a bit. Did they say anything? In fact, we're supposed to find, right? You want to determine the enthalpy change of the reaction, right? And yeah, you want to see the effect of temperature. So looks like at high temperature it shift left because we are supposed to determine the enthalpy change, ma'am. All right. So maybe the temperature was high. It causes the equilibrium to shift left. That's why it becomes less pink. The absorbance is lower and the concentration is lower, ma. All right. So that is what I have written now. Now let's look at what the marking scheme wrote for part 2. They said this. Not all solution B was transferred. Okay, that makes the concentration too low. All right. Now, 1 mark when you circle your anomaly, and the second mark is to explain. Now, class, what is solution B again? Solution B is your thiocyanate. That means they're trying to say that you did not put enough of thiocyanate in. All right, you didn't put enough thiocyanate in over here. This part, you did not put enough here. Therefore, you did not form enough here that appeared lower. Okay, that appeared lower. So that is what the marking scheme is trying to say, because remember Fe3 plus was excess. So you never transferred everything from here. That's why over here, you will never get open 002 max. You will get lower than that. That's why all your numbers will appear lower than expected. Now, I want you to look at examiner report for this particular section, which I managed to secure credit mark, which is 2E2. The anomalous point was identified by most candidates. The reason for the anomaly was less readily understood. That means a lot of students don't understand why. Given that they were told it was not an error in measurement, most candidates found it very hard to reason the anomaly without discussing a measurement. That means a lot of students, when they want to explain anomaly, they tend to blame it on the measurement, where the measurement was taken a bit earlier or later than expected, somewhere along the line. All right. Higher performing candidates suggested that the reaction was not completed. That means not all of the thiocyanate was converted yet, okay? Or it has not reached equilibrium, or not all solution B has transferred. Okay, now other credit-worthy response included the idea that the concentration was too low or the cuvette was not clean. Now, when the cuvette was not clean, cuvette is basically, biology students should know what's cuvette. A cuvette is basically a container, like a test tube, that is put into the colorimeter to measure one. So this is a cuvette, side view, all right, or front view. This is where the light that goes in. Okay, so this is your red color solution where your blood ion thiocyanate here. All right, and this is the detector to detect the absorbance reading. Right, so when your cuvette is not clean, which you have some droplets of maybe distilled water or whatsoever, the light will be scattered off. All right, so therefore the absorbance reading here will become lower than expected. So I think that's correct. If your cuvette is not clean, then the absorbance reading will be lower than expected because light will be scattered off. Okay, and the other one is called the concentration somehow to be lowered. So for me, I managed to secure 1 mark over here, credited. But my answer on why the concentration was lower was not according to what they expected lah. All right. I said that the temperature was somehow higher, which is not my fault. I wanted to run the experiment at the 284 Kelvin, but somehow maybe the experiment was a little bit higher than 284. That causes the equilibrium position to lift. This is my defense. I did run it at 284 Kelvin, but I don't know what happened. Somehow the actual temperature during that particular point of time was a bit higher. That causes my concentration to be lower. How I know the concentration will be low is because all from the table here. Okay, so I still get my credit mark is because I did address lower concentration, but why the concentration was lower, that one I didn't, I mean, it's not necessary lah, because they said credit worthy ni mah, according to the examiner report. See, other credit worthy responses, including this one. All right. So the question now is, what causes the concentration to be too low? I said the temperature was a little bit higher, but the examiner was expecting maybe it had not reached equilibrium, maybe the reaction was not completed. Now, to be honest speaking, do I believe my answer is wrong? The answer is no. I believe my answer also has a probability there. All right. Because all these answers are whether the temperature was higher than expected, whether you did not transfer all the solution of B into it, all right, or whether the cuvette was not clean. All these are speculation. And we don't know actually what is the true reason. All these are probable reasons why the concentration will be lower than expected. So hence, if you don't know what's the correct answer, then why can't my answer be accepted? Correct or not? All right. So for me, when I explain the anomaly, I will normally has a systematic procedure on how I check back what is the error of the anomaly first, and I check back using the table provided to explain, all right, to get a possible explanation, all right, because nobody know what went wrong, but we can come up with a couple of few possibility. Are we clear? So I hope I managed to give you an alternative answers and as well as an insight on how I decipher or investigate on anomaly. I don't just, simply create an excuse out of thin air to explain it, but rather I show you how I find where should you be and what happened to you. And when I know what happened to you, I check back from the table here to find out what happened according to the data. I don't give creative ideas. Rather, my explanation was all checked back by the table. Are we clear? Okay, so therefore you clear what is my opinion and what is the marking scheme version as well. Okay, now next, determine the gradient. I did mention when you want to select two coordinates, please select two coordinates that, at least also 50% apart of the two. All right. What I did was, okay, let's investigate this time. What did I selected? 0.0032 and 0.00295. So basically it's 320 and 294. So let's see where is it. 320. I think I selected somewhere here. I think 320 here. Here, as you can see, my dot is quite obvious here. 320 and 294. I selected here. Okay, geez, it's a bit too small. I violate my law. Okay, never mind. Maybe I should be a bit more cautious. I normally will try to, take a bit. It's just a habit of me. Normally, I won't take so short one. Normally, I'll take something like this. A bit further one. Okay, I normally won't take so short like this. Okay, but nevertheless, examiner, I don't think that until that point, because they never write in the examiner report or the marking scheme on the requirement of the two coordinates. But normally I have a habit of taking at least also 50% of the line. Okay, so give your coordinates and then calculate. So the gradient is positive. I give it to 577, approximately there. Your gradient and my gradient shouldn't run too far. Is because this line is drawn by them. All right, we all have the same line on the same question paper. So it only depends on the coordinates that you have read. Okay, now use the gradient calculator in E3 and equation 2 to calculate the value of enthalpy change. So the gradient is 577, and just now you saw already where is your gradient in the function. This is your gradient. Okay, so your gradient is this. You equate it to your 577, and then after that, what you need to do is you need to divide by 1000. It was my mistake. I didn't realize it was kilojoule. All right, so that's why I've forgotten to go and multiply by 10 to the power of -3. Okay, so therefore the answer should be approximately around -11.04. Like I said, please take note what is your R. Your R over here, let's look over here. R is 8.31. You must use 8.31. Use according to your particular exam series. Sometimes 8.314, sometimes 8.31. You never know. You shall not assume the number for them. Are we clear? Okay. So therefore, this one, I think the discussion is completed.